Okay, so the P-medium with mutual communication is essentially a quadratic assignment problem with one set of constraints removed. And for that reason, it's NP complete. And it turns out that in an important paper by Deering, Francis, and Lau, they proved that this problem is a convex problem for all choices of data, for all choices of the weights and the edge lengths, if and only if the network under consideration is a tree network. That's a very powerful theorem. Of course, to be able to prove such a theorem, first you have to know what you mean by convexity on a tree network. These things are not straightforward because convexity is well defined for Euclidean spaces, but you have to modify or adapt your definitions accordingly for the case of tree network space, okay? Or for network spaces in general. Anyway, that's an important theorem. Based on that, Erkut, Francis, and Lau actually proved that the version with distance constraints that has constraints on the pairwise distances, the upper bounds on the pairwise distances of either this kind or that kind. So with those additional constraints, they gave strong lower and upper bounds on the objective function value based on linear programming. Okay? And Zhu, Francis, and Lau gave a polynomial algorithm that localizes the solution. B is the number of blocks here that you can get from your network. Chajed and Lau, they gave a general network, polynomial time for a general network problem, provided that the interactions between pairs of facilities, either new facility pairs and existing facility pairs, induces a series parallel interaction graph. What do we mean by the graph of interactions? Well, if, let me put it this way, you can create a network with P nodes, each standing for a new facility, and additional N nodes, each standing for an existing facility or a vertex of the original network. And then you connect the node pair Nj and Nk with an undirected arc if there's an interaction. In other words, if this is a positive weight. If it's zero, you don't connect. You don't put an arc. Likewise, you connect Nj and Ei if the associated weight is non-zero or positive. We don't permit negative weights here. So this gives a network whose arc set is defined this way and whose node set is defined this way. And if that's the interaction graph. If that interaction graph happens to be series parallel, then you have a polynomial algorithm for locating your facilities. Now, if you don't know what a series parallel graph is, I'm not going to go into that because that requires a complicated definition. All right, for the case of tree networks, the problem is solvable in polynomial time. And the main contributor for this is the Pickard and Ratliff paper. But prior to that, Deering and Langford, in an unpublished paper, they actually proposed that a tree network can be actually embedded into a higher dimensional Euclidean space so that the tree network distances are essentially the same as rectilinear distances in the Euclidean space. And using the rectilinear distances, actually things can be solved, okay? Because rectilinear location problems of this nature, they've been already solved. That paper is not published. I'm not sure why, but later Pickard and Ratliff showed the problem is solvable in NP cube time for the case of path networks. It's essentially a minimum cut problem. Then Colin, in his dissertation, picked on the Pickard-Ratliff paper's ideas and actually solved the general tree network case, general tree network, not path, but just general tree, in polynomial time. So Colin's important theorem is the following. A given solution is optimal if and only if there is no subset of facilities that can be moved to adjacent nodes and still improve the objective value. That's an important theorem. So no subset of facilities should be moved to some adjacent node and still get improvement. If you get improvement, you're not optimal. If you don't, then you are. So actually, you're characterizing optimality using only local conditions. That's important. Okay? That's because for tree networks, you've got this convexity of the distance playing an important role. So that theorem actually leads to a minimum cut type of solution approach. Minimum cuts are the same as network flows. If you essentially, if you want to solve a minimum cut problem, you just solve a network flow problem, maximum flow problem, and maximum flow problems are solvable in polynomial time. For that reason, things become polynomial here. I'm not going to give you the details. However, if you happen to get interested into in that, I can supply you with lots of details on that, because it's all in my head, actually. It's a pretty good approach, that one. Erkut, Francis, Lau, and Tamir, they solved the problem using math programming. MP stands for math programming. And they used duality and column generation, which is probably something that you are interested in right now, okay? All right, so Tamir also considered the problem with distance constraints and gave a centroid decomposition algorithm, which is again polynomial. Chajad and Lau gave the series parallel interaction version on a tree network. It specializes to an even lower polynomial algorithm. And there's an extension to K-trees later. Now the P-center with mutual communication. Again, in this case, essentially we've got the same situation as the P-medium problem with mutual communication, except that you're trying to minimize the maximum of these distances. So the summations are replaced by max operators, and you pick the maximum weighted distance between facility pairs, either new facility pairs or new and existing facility pairs. And this problem is NP hard on general networks. Again, Colin proved it. Deering and Francis Lau, in the same famous paper, they showed that this problem is a well-defined convex optimization problem if and only if the network under consideration is a tree network. And then Francis Lau Ratliff gave an important characterization for the tree network case. They solved the related distance constraint problem. The related distance constraint problem is the following. find P locations on a tree network if they exist, such that the distance between xj and vi is less than or equal to some given upper bound cji. This is for each ji given in some subset related to the C type of data. Okay? In other words, not all pairs have to be bounded above, but those pairs that are bounded above by a certain finite number, you put them in the constraint. You have similar constraint for new facilities. Again, C's and B's are given positive numbers. Say in some subset relating to the B type of bounds. All right, so, well, when these numbers are given, of course, you may or may not have a feasible solution. If you have a feasible solution. So, your job in this problem, this is called the distance constraint problem, the acronym that I listed on the slide. Your job is to either conclude that there is no feasible solution or else find one if one exists. It turns out that the Francis Lauer-Ratliff paper characterizes the distance constraints by the so-called separation conditions. These conditions are polynomially many inequalities such that if these inequalities are satisfied by the problem data, you have a feasible solution, and actually it tells you also how to go about it. And if they are not, if at least one of them fails, then you don't have a feasible solution. I'm not going to go into the detail, but it's a strong characterization. And based on separation conditions, also they gave a polynomial time algorithm called SLP, or sequential location procedure, which is something similar to the string pulling algorithm that I gave you for the P-center problem. Actually, the string pulling idea comes from that. The original version is the sequential location procedure. Later, myself, Francis, and Lara, we looked at certain equalities in the separation conditions. These equalities define the so-called tight paths or tight constraints, and it turns out that this actually gives lots of additional insight for extending the sequential location problem procedure. Arkut, Francis, and La, they gave the distance constraint problem and used math programming. Chajed and Lara solved the node-restricted version, for which the interaction graph is series parallel in polynomial time. Myself and my master's student Yeşil Kökçen, Bircan, we also solved the distance constraint problem when the interaction graph is a tree, but the actual location space is a general network. So that's a polynomial time algorithm. And Averbach and Berman, they also gave a related sequential location procedure, which is a little bit more general than the earlier one. All right, so this problem is polynomial time solvable on tree networks. It's NP complete on general networks, except that the Tansel Yeşil Kökçen paper gives a polynomial time algorithm for general networks, assuming that the interactions induce a tree type of structure. This is the graph that I was talking to you about. In this example, you have two new facilities you're trying to locate, and you've got three existing facilities, or the vertices. And the interaction between new facility 1 and new facility 2, the weight is 1, or the upper bound is 1, for example. And the other upper bounds are, say, 2 for the given pairs. So in this example, separation conditions tell you the following. The shortest path length between any EI and any EJ on this network should be less or equal, greater or equal the actual distance between Vi and Vj, the actual location. So the separation conditions simply tell you this. The shortest path length, let me just denote it by this, between any Ei and Ej in the interaction graph, where the arc lengths are the upper bounds, either C's or B's, okay? This should be at least as large as the actual distance between the vertices Vi and Vj. And this should be true for all pairs of I and j. So if these are satisfied, so you've got only n squared, order of n squared inequalities like this, and these lengths are computable a priori, of course. All right, so what's the relation between the distance constraints and that one? Turns out that this problem can be expressed in this way. It's an optimization problem of this sort. For any fixed value of z, it's nothing but the distance constraints, of course, as dependent on z. So it turns out that if you look at the interaction graph for given z, the interaction graph is defined only by these pairs in IC and IB, nothing else. So it has nothing to do with z. So interaction graph is just a single graph. And all that happens is, if you take z to be 1 for a moment, forget the optimization, and take these weights, or the reciprocal weights, as your CJIs and BJ case, and form your interaction graph, then using those weights, you have a certain shortest path length between each ij pair. You're trying to satisfy these conditions. That's with these weights. And you want that to be greater or equal this for all pairs of vertices. Now, you want, of course, this may or may not hold for z equals 1, because z equals 1 is a particular choice. However, what you want to do is you want this to be satisfied for any choice of z. When you replace 1 with any z here, what's the relation between the shortest path length for that z and the one with the reciprocal weights? It's going to be z times that, if you can see that, okay? Because if these numbers are the reciprocal weights, if you happen to have z as multiplier, then each of them will be multiplied by a z. So the shortest path length will simply be the same old shortest path length times that common multiplier z. So this actually tells you that you're looking for the minimum value of z such that the conditions that we outlined here hold. Now that is really good, because those inequalities simply tell you that my z is supposed to be greater or equal each of these numbers, and for all ij, So the smallest z I'm looking for should be the largest of these. So your z star is going to be, the optimum z will be the maximum of these numbers. That's a beautiful result. And they solved it by computing z first, z star first, and then just using the sequential location procedure. That's how analysis goes. That's why you start doing something, you finally get somewhere. Don't think too big at the beginning. Well, think big, but proceed slowly, step at a time. Okay. The p-centered ion problem. Some people call it the medicenter problem. Some people call it the centered ion problem. This is a multi-objective problem. Now, I don't know how familiar you are with vector optimization problems, but let me just give you a brief introduction for it. Suppose you have some kind of a single objective problem, such as minimize x in some feasible set, say S. Now, this could be a linear program, integer program, or a network location problem, or anything. Okay? You're trying to minimize a single objective function in some feasible set S. The feasibility could be defined in various different ways. If you have multiple objectives, say two different objectives, two different optimizers, but you're supposed to choose only one solution, X. I'm trying to, for example, well, in that case, of course, one optimizer will use a particular f, the other one will use a possibly different f function. So the x that is minimum for one of the optimizers is not necessarily minimum for the other guy. So you don't know how to go about this. For this reason, when you have f functions related to many different optimizers, say k optimizers, and you're trying to choose a single x, in that case, the problem under consideration is not a simple minimization, but it's a vector minimization problem. You're minimizing the vector function f of x defined by this. Now, the meaning of vector minimization is quite different from the regular minimization. Still x in the same feasible set, okay, which we assume is common to all optimizers. So in that case, well, in this case, what is the meaning of the minimum? You are looking for a point x star in S such that this guy is less than or equal to f of x for all x in S. That's what it means to minimize in the single optimizer case. In this case, what you're looking for is you're looking for undominated or non-dominated solutions. Now, assuming that each is a minimizing type of objective function, if you have 2 points, say x and y, both possible solutions, if you evaluate f, this is a vector, and at x as well as at y, if it turns out that this vector is less than or equal to the other vector in each component. So since you're trying to minimize everybody, obviously this is doing something good. Okay? And in fact, if it is also strictly better in at least one component, so not equal means they are not actually equal. Some component is strictly less than the corresponding component of the other guy. So in that case, such a solution is called a non-dominated, or, sorry, it's not called, then x dominates, let's do it first this way. And X dominates Y. Why? Because the performance of the point or the solution X in each objective is at least as good as the performance of the other point, and it's strictly better in at least one. Okay, so X is certainly not inferior to Y. Okay, this is if you already have a pair of solutions. So it turns out that a point X in S is non-dominated some people call efficient or Pareto optimal if there does not exist U in S such that f of U is at least as good as f of X and strictly better in at least one component. So, in other words, X is non-dominated if there is no other point that dominates it. Okay, I already gave you the definition of what dominating means. Now, these things sometimes take a while to process, so don't worry if you did not quite make it, digest, because sometimes it takes a while. Yeah.
If it's not true for all u, then doesn't that mean that f of x is less than or equal to for all u?
No, it doesn't mean that. No, this simply says that there's no u which dominates x in the sense I defined it. But it simply means, it doesn't, x can dominate certain things, but may not also dominate other things, okay? For example, just to answer your question, you could have two different solutions where fi of x could be less than or equal to fi of y for I in some index set, say I1, but yeah, it could be this way. In the remaining index set. And maybe one strict inequality in one of them, okay? So there's no relation. This is a partial order, okay? Yeah.
So for this case, both x and y are efficient?
In which case? We don't know. We don't know.
Well,
neither one dominates the other one.
Yes.
We can only say that, but they could be efficient or may not be efficient. It depends on all the rest, okay? If there's in order for a point x to be efficient, you have to consider the rest of the points.
Yes, I mean, if there are 2 points and those 2 points have those kind of relations.
Oh, I see. If there are only 2 points in the set S, then of course, in that case, they are both good. Yes, they are both efficient. Yes. Yeah. Mm-hmm. So the main idea in vector minimization is to find the set of efficient solutions. That's what you're looking for. And in the context of the P-centodion problem, you're looking for a P facility point set. You've got 2 objectives. One is the minimax objective. The other one is the mini-sum objective. One is the median type. The other one is the center type. That's why it's coined as centodion. Okay. All right. So Halpern is the first one to consider the. Yes.
Is it always possible to find such points like not dominate or efficient?
Yes. Yes. It is. For a 2 objective case.
Let's say.
For a 2 objective case. Suppose this is the objective value for the first one, this is the objective value for the second one. I'm looking at the objective space, not the point set. Now, there could be many values here, you know, whatever. So these are the set of points z1, z2, such that z1 is z2 is defined by some x with f1, f2 with x in S. So this is that set. Okay? These are all possible two tuples of objective values. Let's assume it's a continuous space. Now, when you look at a particular x point whose z1, z2 value happens to be this and that, this guy is good. Because if you wanted to decrease the z1 value, you have to go this way, but then you're necessarily increasing z2 value because you have to move along this. Okay? You see that? Let me take an easier case. Look at this, for example. This one is not an efficient point. Why? Because I can certainly find other points without changing z2 value, but still decreasing z1. You see? So I hit here. Now, with this point, I can no longer do that because as soon as I try to decrease that, I have to increase the other one. Okay? So you can see that the efficient set of objective values for this example will be these. And so the points points x in S that induce these z1, z2 two tuples will be efficient. Anything else will not be efficient.
Let's take 2 points.
He had a question first. Yes.
I couldn't catch that point.
I know, because it's too fast. Yes.
What if minimizing z1 is more important than minimizing z2?
No, we're not assigning value judgments to these. In that case, if you are able to compare the two objectives in terms of weights W1 and W2, then what you do is you minimize this, which is a single objective function. Okay? Actually, the summation is not needed there. You see, if you know the relative weights, then you just combine them in a weighted way, and then you just minimize a single objective function. But typically, you don't know what these weights are. Okay? Yes?
Let's take 2 points. One of them is the solution of p-centered, optimal solution, and one of them is the optimal solution for p-median. Like, then we have two tuples, and we know that one of them
cannot be made any smaller.
Yeah.
So those two solutions will certainly be efficient because one of them cannot be made any better. However, let me point it out this way. Suppose you've got alternative P1 or P-median solutions. Let's take the P equals 1 case. Suppose you've got two adjacent nodes that are equally good, okay, for solving the one median problem. Now, when you look at the one center objective, one can be inferior than the other one. Okay? So in that case, only one of them is an efficient solution, the one that gives the smallest value also for the center solution. Okay? Does that make sense? Okay. Yeah. All right. So I know this was kind of too fast because it takes a while to absorb these things, but believe me, this was the shortest crash course I gave in vector optimization. At least you have an idea, okay? If you think about it, it'll come after a while. Halpern also considered the same thing on trees and showed the equivalence of the constraint version and the convex combination problem. In the convex combination problem, you're assigning a weight of, well, say lambda to one of the objectives and 1 minus lambda to the other one. Okay, you assume your weights are adding up to unity. So it's a convex combination of two objectives, and you parametrically search over lambda, okay, as lambda varies between 0 and 1. In the constraint version, you try to minimize one of the objectives and put the other one as a constraint. In other words, the objective value of the second one should be less or equal to some known parameter. And then you parameterize on the right-hand side. All right, so Handler considered this problem on trees and solved the constraint version, etc. You've got some other things, but the most important thing here is that there are actually, it certainly makes sense to consider sometimes multiple objectives, okay? Now, in the case of, for example, emergency facility location, my basic tendency is to totally concentrate on human life. Forget the cost. I mean, you do it at whatever cost, okay? But if you're actually dealing with something very, very costly, then you do have to consider the cost aspect as well, okay? So in that case, a multi-objective approach could be perhaps more meaningful.
Maybe the example is not the emergency for human life, but repairing something, providing a repair service. You have to consider both time and cost.
I see. Okay, yeah, that's a reasonable example. If you have a repair service, you want to get there fast, but you also want to make it economical. Yeah, good. Thank you. That's a good example. But I'm not sure if the actual repairers actually care that much about that. The company owner probably cares about that, but they don't really seem to care too much. The robust median, well, I'm not going to go into it because we are out of time, but you have a fairly good idea of at least what the literature involves until these days, okay? Robust median is also a very interesting problem when you don't know the actual weights as point values, but you know, say, intervals on them. Then how do you solve the problem? That's an interesting question. Apparently, I was the first one to consider that problem. I started looking at that problem back in '86. Then I had a German student from Schauenstuhl from Germany who actually wrote a master's thesis on that with my input. And we solved the one median problem with interval weights in that paper, except that we never published it. Later on, some other interesting stuff also came out, but unfortunately we don't have time to go into it. Okay, so that's it. I hope you enjoyed the class, and anyway, if you have questions, you can come to me later, okay?